Hello everyone, welcome back to Spectrum classes. This video is in continuation with the LS and JJ coupling. Here in this video we are going to discuss about the determination of term symbols for different type of electrons based on LS coupling. Since this LS coupling is applicable for the atoms which are having less atomic number, and sometimes it is mentioned that those atoms which are having their atomic number less than 30. For different type of electrons, this LS coupling is applicable, and we are going to determine the term symbols for them based on their electronic configuration. So here different type of optical electrons. So first I'll just tell you what is called optical electrons. So optical electrons are those for which we are going to determine the term symbol. Here there are three different type of optical electrons. One electron system where only one electron is present. For example, S1 system or P1 or D1, etc. So only one electron is there for which we are going to determine the term symbol. The next type of electrons are non-equivalent electrons. So non-equivalent electron means the electrons which are present in different orbitals. For example, here one electron is present in s orbital and the other electron is present in p orbital. So these are non-equivalent electrons. And the third type of electrons are equivalent electrons. So what kind of electrons are known as equivalent electrons? For example, p2 and d2. The electrons which are present in equivalent orbitals means the orbitals which are having same value of principal quantum number n and azimuthal quantum number l having same values are known as equivalent orbitals, and the electrons which are present in the equivalent orbitals are known as equivalent electrons. So there are three different type of combinations for which we are going to determine the term symbols. Here I'll just give you the all type of examples one by one. So first we are going to determine the term symbol for one electron system. So here suppose I am having S1 system, means there is an s orbital which is having one electron. So how we are going to determine based on this electronic configuration, right? So here L is the total angular momentum, S is the total spin angular momentum, and J is the total angular momentum. So first we are going to determine the L value. For one electron, the orbital angular momentum for one electron is equal to the total orbital angular momentum. So here what you have to do first, for this write the azimuthal quantum number. So L is equal to 0 for this S. For P it is 1 and for D it is 2, etc. and so on. This L is equal to this L, right? So here total orbital angular momentum is equal to the orbital angular momentum for the one electron. So this is again equal to 0. The next thing, we now assign the state for this total orbital angular momentum. So here this capital L is equal to 0. It means it is of S state. The next step is to determine the S or total spin angular momentum. So here this S is equal to summation of S. So for this one electron we are having 1 by 2. So total spin angular momentum is equal to 1 by 2. So using this spin angular momentum we now calculate the multiplicity. So multiplicity is equal to 2s plus 1, which is equal to 2 into 1 by 2 plus 1. This gives us 2. It means it is doubly degenerate, right? Now coming to the J. J is total angular momentum or spin orbit coupling. This J has values L plus S to L minus S modulus. So here first what you will do, L plus S. What is L? L is your 0. And what is S? S is your 1 by 2, this capital, right? So 0 plus 1 by 2 is equal to 1 by 2. And 0 minus 1 by 2, again you are having 1 by 2. And there is no value in between. So only 1 by 2 value is there. Now how to write the term symbol? So here is the way we can write the term symbol. So first write the total orbital angular momentum corresponding state. So here S state is there. S. Then put multiplicity. So multiplicity is equal to 2. Write 2 as a superscript on the left hand side. Now on the right hand side put J as a subscript. So J is having 1 by 2 value. So here this is the term symbol for this 1s electron. So this is how one can determine the term symbol for S1 type of electron. Now I'll just take one more example. Suppose I am having P1, right? So for P, what is our L? L is equal to 1. For this one electron, small s is equal to 1 by 2. Now capital L is equal to L for one electron, and this is equal to 1, and corresponding to this we are having P state. This is capital, this is small. S is equal to small s is equal to 1 by 2, and corresponding to this multiplicity is equal to 2s plus 1. So 2 into 1 by 2 plus 1 is equal to 2 again. Now coming to the J value, J is equal to L plus S2, L minus S differing by 1, right? So I am not writing that. Here L is 1, S is 1 by 2. L is 1 minus S is 1 by 2. So we get 3 by 2 and 1 by 2. So in between, if we just write 1 plus 1 by 2 minus 1 by 2, so we will get 1 by 2. So no value differing by 1 between these, right? So we are having two values of J. Now the term symbol for this P1. Term symbol for this P1 will be 2, 2 as the multiplicity here. You just see P, this one, and these are the J values. So J is 3 by 2 and 1 by 2. So this is the term symbol. Here it is split into two energy levels. So this is how one can determine the term symbols for one electron. Now coming to the two electron system. So for two electron we are having two different type of cases. One is non-equivalent electrons and the other one is equivalent electrons. So here we are going to discuss about the non-equivalent two electrons. Non-equivalent electron means both are present in different type of orbitals. So here we are having S1 and P1. So what we are going to determine here? So first we are going to determine the L, or total orbital angular momentum. So here total means the sum of orbital angular momentum for this first electron and the orbital angular momentum for this second electron. So let's start. Here L1 is 0 for this S electron. L2 is 1 for this P electron, right? Now we are getting the value of capital L, which is known as total orbital angular momentum, and which is having value L1 plus L2, L1 minus L2 differing by 1. So here L1 plus L2 is 1 and L1 minus L2 is again 1. So we are having only one value for this. The next is we are define the state for this. L is equal to 1. So for 1 it is having P state. If you have any confusion, so here I am writing again. L is equal to 0 stands for S, L is equal to 1 for P, and L is equal to 2 for D, and so on, right? And for states, capital L, or total orbital angular momentum, if it is 0, then it is having state S. If L is equal to 1, it is having P state, and if L is equal to 2, it is for, and so on. In this manner, we are going to assign. So here again, I am telling you, this is S. So L1 is 0 and P, L1, L2 is 1. Fine. So if we are getting L is equal to 1, then it stands for P state. Now determining the total spin angular momentum. So S, for first electron, we are having half spin. For second electron, again we are having half spin. So total spin correlation is this capital S is having values S1 plus S2 to S1 minus S2. So I'm just writing S1 plus S2. It gives me 1. S1 minus S2, it gives me 0. Differing by 1, no value is there. From this S, we are going to calculate the multiplicity of the state. So multiplicity is 2S plus 1. So put 1 here. In this case, we get 3. And if we put S is equal to 0, then we get 1. So we are having two different states. One is triplet degenerate and the other one is singlet. Right. Now coming to the J value. So J is having values L plus S to L minus. Here L is 1. S is two sets are there, 1 and 0. So first we are going to take the case L is equal to 1 and S is equal to 1 since S has two values. So first I have taken these two values. Now according to these values, L plus S gives us 2 and L minus S gives us 0. And since it is differing by 1, so 2, 1, 0 will be the values of this J. The second case is L is equal to 1 again and S is equal to 0. And for this, L plus S gives 1, L minus S again gives 1. So only one value is there. So according to this, we are going to write the term symbol. So here, first write the state. So state is P. Here, I have written this. So here, P is the state. So I have written over here. 3 is the multiplicity corresponding to this S1. So 2S plus 1 is 3. And according to this L and S, we are getting three values 2, 1, 0. And for this, we are getting the another term which is 1p1. P stands for this L is equal to 1. And for multiplicity, we are having 1, 2s plus 1. And J is this. Here we are having four different terms. So it can also be written like this. 3p2, 3p1 and 3p0. So it splits in three energy. It splits in one only. So in my previous lecture, what I said, if the value of L and S, we are having 2S plus 1 or 2L plus 1 splitting levels. So here, according to this, we are having three splits. Here we are having 3. And according to this, here S is less than, so 2S plus 1 again. So only one splitting level is there. That I mentioned in my previous video. So that is the possible values of J. This is how one can determine the term symbols. We can also have another examples. For example, if I take the example of P1 type of two non-equivalent electrons, how we are going to solve and what will be the term symbols for this type of electronic configuration. So first we are going to determine that. So I hope guys you understand. For this L1 is equal to 1 and for this L2 is equal to 1 and these are the half spins. Spin 4, this is S2 1 by 2 and this is S1 is equal to 1 by 2. So from here we are just going to calculate the total orbital angular momentum and total spin angular momentum. I am going to show you. You just see this. L1 is 1, L2 is 1. Then total orbital angular momentum will be having values L1 plus L2 to L1 minus L2. So L1 plus L2 will gives us 2 and L1 minus L2 will gives us 0. So from these two extremes, we can calculate this is 2 and this is 0. And rest are the values are differing by 1. So 2 minus 1 will be 1. 1 minus 1 will be 0. Only three values are possible here. According to this total orbital angular momentum, we are now assigned the states. So here for this 2, we are having D states. For this 1, we are having E state. And for 0, we are having S state. So we are having three different types of states. Now calculating the total spin angular moment. So as I told you earlier, S1 is equal to 1 by 2, S2 is equal to 1 by 2. So corresponding to this S1 and S2, we are having total spin angular momentum values S1 plus S2 to S1 minus S2. So we are having again 1 and 0 values. Corresponding to this total spin angular momentum, we are going to calculate the multiplicities. So for S is equal to 1, we are having triplet. and for s is equal to 0 we are having singlet. Now according to this we are going to calculate the total orbital angular momentum value J. So J is having values L plus S to L minus S. So here we will take the case number 1. L is 2 and S is 1, right? Corresponding to this we are having three values L plus S 3, L minus S 1, and in between we are having 2. The second case, L is equal to 1 and S is equal to 1 again. So according to this, we are having 2, 1, 0. 1 plus 1, 2, 1 minus 1, 0, and differing by 1. So 2 minus 1 is equal to 1, 1 minus 1 is equal to 0. The third case is L is equal to 0 and S is equal to 1. We get values equal to 1. Similarly, for L is equal to 2 and S is equal to 0, we are having 2, and for L is equal to 1, S is equal to 0, we are having 1, and for this we are having 0. Now assigning the term symbols according to these values. So for L, we are having D. And here is the multiplicity corresponding to this one, and here is the J values or total angular momentum. It has three splittings, three energy levels, right? Or this term splits into three. Similarly, for this, we are assigning the term symbol 3P210. So, according to this one, we are having P. According to this, we are having P, and this is A value. Corresponding to this, we are having this, and these are the term symbols. I hope you are able to write down all such term symbols now. Here, again, I am telling you for 2, it is D, for 0, it is 1 multiplicity, and this is the J value. So for P1 system, we are having this many term symbols, right? Now coming to the energy order of these term symbols, and what about the equivalent electron? So guys, if we are having two electrons and that are equivalent electrons, then what will be the case? So first of all, I must tell you, if we are having two non-equivalent electrons, this many term symbols are possible, which I solved in my previous slide. But for two equivalent electrons, only this many term symbols are possible. So what you have seen, many of the term symbols are not allowed for equivalent electrons. That is important to understand. For this, we are having all possible values, but for P2 or equivalent electrons, only some values are permissible, rest are not possible. This is because we are here following the Pauli's exclusion principle. For two electrons, all four electrons cannot be same, as well as Hund's rule of maximum multiplicity. So this P2 system I will solve in my next video. Now coming to the ordering of these energy levels. The order for these energy levels will be done in this manner. So three things are there. First, go for the highest value of S, means maximum multiplicity is the lowest one. So here maximum multiplicity, first find out the multiplicity here. So here in this case, this is 1, this is 1, and this is 3. So this is the highest one. So this will be the lower value of energy. Second, coming to the largest value of L. So first we decide the multiplicity. The largest L value lies lowest. So here, if we are having multiplicity same, then the term which is having high value of L, that will lies lowest. So here this is applicable. So 3P is the lowest one, then 1D is the lowest one. Now coming to the J value. If the multiplicity and the L value both are same for the term, then what will be the lowest energy level? So the level which is having smallest J value, that lies lowest. So here we are having 0. So this is lies lowest. So in this manner we have to arrange this. So to determine this, the highest value of L, largest value of L, and smallest value of J. The reason behind this smallest value is that we are having the magnetic field direction in the field of L, and its magnetic moment is opposite to this, so mu L is in this direction. If we are having spin angular momentum in this direction, then its mu s is again in this direction. So mu s are coupled together is not favorable. So high value of J is not of low energy. If we are having the another case when this this is the B, this is the L, and this is the mu L, and here is the mu S, and here is the S, right, vector S. So if this is the case, then their mu s are in opposite direction and they couple together favorably. So low value in this case, when L and S are opposite in direction, then we get the lowest value of J. So this lowest value of J is of low energy. So this is the reason actually, but you can memorize these terms by strong coupling of S, strong coupling of L, and small coupling of J value. So strong and small, which I have discussed in LS coupling previous week. So more S, more L, and less A. So this is the trick how you can memorize. In my next video, I am going to discuss the states and microstates which play a vital role in case of equivalent electrons. So I am going to discuss in details in that video. I hope you understand the concept which I have discussed here in this video. If you like this video, please subscribe my channel, give me a thumbs up. Thank you all. Thanks for watching.